Hello, welcome to the another lecture Control System and Instrumentation. I am Mr. Prajit from Asansol Engineering College. I like to giving you some numerical concept regarding time domain specifications. Already from lecture 1 to lecture 8 respectively, I discussed several fundamental things which are regarding to control system. I discussed what are the types of feedback system, that is negative feedback, positive feedback, how to determine transfer function based on block diagram reduction technique, as well as signal flow graph depending on Mason's gain formula. Even I analyzed how to determine transfer function for different type of appliances, that is room heater system, for electromechanical system, and even already we have represented an analogous system. That means suppose I am providing one mechanical system, and what will be the equivalent electrical circuit for that, and vice versa. That thing is also analyzed. Even I mentioned about the Routh-Hurwitz criteria to determine the absolute stability of the given system. Now I need to discuss about some numericals regarding to time domain specifications, and these thing will be highly illustrated when I will teach to you people on the lecture 13 respectively. Okay, now see, the respective problem is for the control system shown in figure, determine K which satisfies the following requirements. Number 1, A is maximum percentage overshoot, that is PO is equal to 10%, and B is the 5% settling time for TS is equal to 1 second. Corresponding forward path transfer functions are provided, that is for the unity feedback system. One transfer function is K by S plus A, another is 1 by S plus 2, and according to the block diagram reduction concept, you know how to cascade these two blocks at a time. Those are in series nature, and subsequently our next aim, we have to determine the total transfer function, that is C of S by R of S, that is nothing K by S plus A into 1 by S plus 2 divided by 1 plus K by S plus A into 1 by S plus 2. That generates, after simplification, K by A square plus S into A plus 2 plus 2A plus K. Okay. Now, what is the formula for maximum percentage overshoot or peak overshoot? That is nothing, that is e to the power minus xi pi by root under 1 minus xi square. Xi is your damping ratio. Xi determines the damping ratio. So again, just recall that concept, that is when xi is equal to 0, it signifies no damping, that is oscillatory nature. When xi is equal to 1, it signifies critical damping. When xi lies between 0 to 1, it signifies under damping, and when xi is greater than 1, that is over damping. So the question is, when peak overshoot occurs? Only when the system is under damped condition, that means xi value lies between 0 to 1. So subsequently we can determine the xi value from the same, because they are wanting, see, determine the K for which the system satisfies the following requirements. Here they are mentioning maximum percentage overshoot is given 10%. So that should be equal to, that means e to the power minus xi pi by root under 1 minus xi square should be equal to 10 by 100. That generates xi is equal to 0.6. Obviously it promises that system is in under damped condition. Now for 5% settling time, that is TS, the respective formula is TS is equal to 3 by tau S, that is 3 by xi omega n is equal to 1, because they are mentioning when settling time is 1 second. And from that scenario, already we are evaluated xi value, that is 0.6. That's why omega n is nothing, undamped frequency, that is omega n is equal to 5. Now if we are comparing these expression, that is C of S by R of S is equal to K by A square plus S into A plus 2 plus 2A plus K, with the help of the standard form of second order control system, that is transfer function, that is omega n, C of S by R of S is equal to omega n square divided by A square plus 2 xi omega n s plus omega n square. Then subsequently we can replace those values. That means if we are tallying, if we are comparing the denominator expression a square plus s into a plus 2 plus 2a plus k with the help of that expression a square plus 2 xi omega n s plus omega n square, then we can rewrite after comparison a plus 2 is equal to 2 xi omega n and 2a plus k is equal to omega n square, and omega n is value 5 rad per second, that's why omega n square is equal to 25. Now, and xi value is already provided, omega n is provided, and then the two linear equations are available. So first linear equation generates a plus 2 is equal to 6, a is equal to, that's why 4, and subsequently we can write from after evaluation of a, k is equal to 70. Now, for higher order systems, the natural response of higher order systems consists of a sum of terms, one term for each characteristic root. Number one, for each distinct real characteristic root, there is a real exponential term in the system natural response. Number two, for each pair of complex conjugate roots, there is an exponential sinusoidal term. Yes, that is another important thing. Again I am repeating, for each pair of complex conjugate roots, yes, that should be arised in case of underdamped situation, there is an exponential sinusoidal term in the system natural response. Number three, repeated roots give additional terms involving power of time times the exponential. Now, for example, if we are looking that for higher order systems, analyze the system with the following transfer function. T of s is equal to minus 8a square plus 5 divided by s to the power 4 plus 9s cube plus 37s square plus 81s plus 52. That can be rewritten in the form as is equal to minus 8a square plus 5 divided by, after factorization, it or after partial fraction nature, whatever, or you can use the one of the most sophisticated technique, that is calculus of residue. So by which you can generate that thing is coming minus 8s square plus 5 but divided by s plus 1 into s plus 4 whole into s square plus 4s plus 13. And obviously, since they are not at all mentioning what type of input will be provided, so by default we will take unit step input, that means r of t is 1 and r of s is 1 by s. Then see, applying the partial fraction, its response is given by, so one thing, see, if you are doing in such a way, you can do it. Otherwise, the best thing for generating the partial fraction coefficient, whatever the partial fraction is, try to do it with the help of calculus of residue. Okay, that promises very good thing for whatever whether the complex scenario you can occur, you can do it in very easiest way. Now see, we can rewrite as c of s is equal to 1 by s. 1 by s, again I am telling, that is nothing, the Laplace transform of the unit step. So 1 by s into t of s. So we can represent the above expression with the help of the partial fraction nature, that is equal to k1 by s plus k2 by s plus 1 plus k3 by s plus 4 plus k4s plus k5 divided by s plus 2 whole square plus 3 whole square. Now, applying inverse Laplace transform on both sides of the given equation, that generates c of t is equal to k1 plus k2 into exponential minus t plus k3 into exponential minus 4t plus a is another constant which clubs the constant of k4 and k5 respectively, that's why I am denoting that is a exponential of minus 2t multiplied with cosine of 3t plus theta. Theta is nothing, that is my argument, that is angle, and theta is, that should be generated with the help of s plus 2 whole square plus 3 whole square. Now, another example for higher order systems, analyze the system with the following transfer function. T of s is equal to minus 7s cube plus 6s square plus 9s plus 23 divided by s plus 1 into s plus 3 into s square plus 4s plus 13 into s square plus 8s plus 17. So we see here the order of the system is 6. It is a 6 order system. Okay, and you people know how to evaluate the order of the given system. Order can be determined with the help of the denominator, and highest power of s determines the order. So in this scenario, if you are looking to the denominator of the given transfer function t of s, here the highest power of s is 6. That's why we can speak the order is 6th order equation, but type is 0 because no 1 by s term is available. So type 0, 6th order system. Keep in your mind this is. Now, so again we can put unit step input to generate the respective response for the same. So we can rewrite, because r of t is equal to 1 unit step, so that's why r of s is 1 by s. So c of s is nothing 1 by s into t of s, and with the help of the partial fraction concept, then we can equivalently represent that k1 by s plus k2 by s plus 1 plus k3 by s plus 3 plus k4 s plus k5 by s square plus 4s plus 13 plus k6s plus k7 divided by s square plus 8s plus 17. And after applying the inverse Laplace transform on both sides, we can generate c of t is equal to k1 plus k2 into exponential of minus t plus k3 into exponential of minus 3t plus a1. a1 is the clubbing of coefficients k4 and k5 respectively. a1 into 1 by root under 1 minus i1 square e to the power minus i1 omega n1 t, omega n1 t cosine of omega d1 t plus theta 1. Here omega d is nothing, that is damped frequency, and omega d, the relation between omega d, omega n and xi is nothing. Omega d can be written as omega d is equal to omega n root under 1 minus xi square. So that should be in your mind. Okay, omega n is the undamped natural frequency plus theta 1 is the respective argument for the same, plus a2 is nothing, that is the constant which clubs those values k6 and k7 respectively, multiplied with 1 by root under 1 minus xi2 square exponential of minus xi2 omega n2 t multiplied with cosine omega d2 t plus theta 2. And here see, we are mentioning the respective natural frequencies as omega n1 is nothing, that is root under 13, because already we are telling the denominator of that portion, that is k4s plus k5 divided by s square plus 4s plus 13, with the help of that standard form of transfer function for second order control system is equal to omega n square by s square plus 2 xi omega ns plus omega n square. So in this scenario my omega n square is 13, that's why omega n is root under 13, that is 3.6 radian per second, and xi1, that is 2 xi omega n, 2 xi1 omega n is 4, that's why xi1 is equal to 4 by 2 omega n, that is 0.55. And another term for k6 k7 related term, omega n2 is root under 17 is equal to 4.12 rad per second, and xi2 is equal to, because 2 xi omega 2 is 8, that's why xi2 is equal to 8 by 2 omega n2, that is 0.97. So in such a way we can evaluate the respective damping ratio as well as undamped natural frequency. Undamped natural frequency is omega n, damping ratio is xi. Now see, already in case of Raoult-Harvey's criteria, before entering that I mentioned about the stability concept, and there I told you people about the S plane. S is nothing, that is sigma and j omega. Sigma should be available along x-axis, j omega plus minus j omega should be available along y-axis, and already I mentioned if all poles lying on the left half of S plane, then we can speak that system is stable. If any pole lying on the RHS of the S plane, then the system is unstable. If no pole lying on the RHS of the S plane, but few pole lying on the imaginary axis, can some pole lying on the left hand side of the S plane, then we can speak that system is critically or marginally stable. And see here, when the pole lying on the imaginary axis, obviously the nature of the system is in oscillatory. That should be all of you known. Now see, when the poles lying on the left half of the S plane, that sinusoid, that means the output response is nothing, that is amplitude is going to be reduced, that means it is the damped sinusoid, that means it will be multiplied with e to the power minus xi omega nt into sine of omega dt plus theta. In such a way it will be going on. That means it is actually decaying nature. And if any poles or all poles lying on the right hand side of the S plane, then see what things are going on. That is, see the right hand side diagram, extremely right hand side diagram, it is nothing, that should be e to the power plus xi omega nt multiplied with sinusoidal omega n dt plus omega dt plus theta. That means the amplitude of the exponential terms should be increased nature. So that is the scenario. That means system is going to be unstable, and poles lying on the imaginary axis means see it is in oscillatory nature. So the respective characteristics are already highlighted to you people. That should be known to you people. Okay. Now another example. Consider the system following in the figure where damping ratio is 0.6 and natural undamped frequency is 5 rad per second. That means omega n is 5 rad per second, J is equal to 0.6. Obtain the rise time Tr, peak time Tp, maximum overshoot M suffix P, and settling time 2% and 5%. Criterion Ts when the system is subjected to a unit step input. Yes, R of t is 1, that's why my R of s is 1 by s. So that is they are provided. Subsequently I am telling to if they are not at all mentioning what will be the input, by default you can take for convenience as a unit step. Okay, and you should mention that same. Now the respective diagram is provided below. Here see the forward path transfer function is provided, that is omega n square by s into s plus 2 xi omega n. Obviously that is the critical damped situation actually. So in this occasion what things are going on, your J is already mentioned, that is 0.6 and omega n is equal to 5 rad per second. So what is the rise time concept? Here see Tr, the rise time formula that should be analyzed on the lecture 13. Again just to recall that thing, that is Tr is equal to pi minus theta, that is divided by omega d, and theta is equal to tan inverse of omega n root under of 1 minus xi square divided by xi omega n. So omega n mutually cancel, that generates theta is equal to 0.93 radian, and Tr is equal to nothing, that is after substitution, that means Tr is equal to omega d is nothing, omega n root under, here see square root is missing, that's why it will be omega n root under of 1 minus xi square, keep in your mind. So it will be Tr is equal to 3.141, that is pi value, minus theta divided by omega n root under 1 minus xi square, that generates 0.55 second. Peak time formula Tp is equal to pi by omega d, and pi value is 3.141 and omega d is 4, that generates 0.785 second. Okay. Now settling time for 2%, Ts is equal to, the formula is Ts is equal to 4 by xi omega n, that's why Ts is equal to 4 by 0.6 into 5, that is 1.33 second, and when it is 5%, then Ts is equal to 3 by xi omega n, that is 3 by 0.46 into 5, that generates 1 second. Maximum overshoot M suffix P is equal to e to the power minus xi pi by root under, it should be root under 1 minus xi square, so that is nothing, that is generating 0.095. so percentage of the overshoot, peak overshoot is 9.5% when multiplied with 100. Now another example. For the system shown in figure, determine the values of gain k and velocity feedback constant kh, so that the maximum overshoot in the unit step response is 0.2 and the peak time is 1 second. With these values of k and kh, obtain the rise time and settling time. Assume that J, that is the moment of inertia, is equal to 1 kg meter square, and B, that is the damping constant or damper, is equal to 1 Newton meter per radian per second. Here the respective blocks provided. The forward path transfer function is provided, that is k by js plus v. The reverse path is kh. Another block is introduced in accordance with the same, that is 1 by s. What is the scenario? We have to determine the values of gain k and kh depending on those overshoot and etc. Now your first job, you just apply the block diagram reduction formula. That means you will eliminate this negative feedback path k by js plus b and k, that should be, these paths should be eliminated with the help of the elimination feedback path, and then you can cascade with 1 by s, that generates the respective forward path transfer function is k by s into js plus b plus k into kh. Then after elimination of the unit feedback, then it generates c of s by r of s is equal to k by js square plus b plus k into kh whole into s plus k. So this is the actual transfer function, total transfer function for the above diagram. Now see, what are the values they are provided? J is equal to 1 kg meter square and B is equal to 1 Newton meter per radian per second. So you can substitute those, that generates C of S by R of S is equal to K by A square plus 1 plus K each whole into S plus K. Then you can compare these expression with the standard form of second order control system transfer function, that is C of S by R of S is equal to omega n square by A square plus 2 xi omega ns plus omega n square, where omega n square can be tallied with k, that is omega n is equal to root under k, and xi is equal to 1 plus kh by 2 root k. Already I discussed on the previous example. These are the comparison result. Now see, since they are provided maximum overshoot is 0.2, so we can rewrite as e to the power minus xi pi by root under 1 minus xi square is equal to 0.2, and taking natural log because exponential is there, after taking natural logarithm it generates xi is equal to 0.456, and since the peak time is 1 second, so Tp is equal to pi by omega d, so 1 is equal to 3.141 divided by omega n root under 1 minus xi square, so omega n generates 3.53 radian per second. Now xi is equal to 0.456, omega n is equal to 3.96 or 53, whatever else it may be, that is radian per second. So omega n is equal to root k, so k is nothing 12.5 after substitution. And since here see, and since xi is equal to 1 plus kh by root under 2 by 2 root k, so obviously xi value is 0.456 is provided into 2 root k is root under 2 12.5 is equal to 1 plus 12.5 into kh, so kh is equal to 0.178. So these are the two values which are they are wanting from your respective example. Now again see, what is the rise time concept for that? Xi is equal to 0.456, omega n is equal to 3.96 radian per second, so Tr is equal to pi minus theta by omega n root under 1 minus xi square, it will be 0.65 second after substitution of all those values. Ts is equal to, that is settling time for 2%, that is 5% is 3 by xi omega n, that is 1.86 second, and for 2% it will be 4 by xi omega n, it is 2.48 second. That should be in your mind. Okay. Now another example. For figure 1, here determine the natural frequency omega n and the damping ratio xi for the transfer function T of S is equal to x of S by f of S. If mass m is equal to 1 kg, b is equal to, that is the damping constant is equal to 4 Newton second per meter, and k spring constant is 10 Newton per meter. Now see, already I taught you people regarding the analogous system where mechanical system is already mentioned, even the how to determine transfer function for the mechanical system is already analyzed. So taking concept of that, we can establish the differential equation for this given system. So we can write as m d2x of t by dt square plus f suffix v dx of t by dt plus kx of t is equal to f of t. Here see, d2x dt square is nothing, that is my acceleration, so mass into acceleration is force, and f suffix v is the damping constant, so dx of t by dt is the velocity, and k is the spring constant, and x of t is my displacement. So after applying Laplace transform on the above differential equation with zero initial condition, because we need to generate the transfer function that generates x of s by f of s is equal to 1 by m s square plus f suffix v into s plus k. Again I can arrange as numerator and denominator by 1 by m divided by s square plus f suffix v by m into s plus k by m. Then I can tally that expression with the help of the standard form of second order control system. That's why we can write as omega n square is equal to k by m, and omega n is equal to c, that is root under k by m, that generates, that is nothing, that is k here c, that is the 10 radian per second, that is actually m is equal to 1, that's why we can write as root under 10 radian per second. So actually this is root under 10 radian per second, and 2 xi omega n is nothing, that is a v by m, so m is already 1 kg, so xi is equal to 2 by root 10, that generates the respective value. Okay. Now another example, for example, that is RLC series circuit is provided. Determine the natural frequency omega n and the damping ratio xi for the transfer function T of S is equal to I of S by E of S. I of S is nothing, that is the respective current, and the E of S is the respective voltage. The closed loop transfer function is provided. Already you are very much familiar about the electrical circuit. Directly we can apply those. So I of S by E of S is nothing, that is 1 by of R plus Ls plus 1 by Cs. That is all of the Laplace equivalent passive parameters. So Laplace equivalent of inductor is SL, Laplace equivalent of capacitor is 1 by Cs. That's the scenario. So when you are generating the transfer function, so it is providing us, that is I of S by E of S is equal to Cs by L Cs square plus RCS plus 1. Then if I am taking common 1 by L on the numerator and the denominator, it will be S by L. That means it will be S by L. That means I am dividing numerator and denominator by LC. So it is generating 1 by L into S by S square plus R by L into S plus 1 by LC, and omega n is equal to 1 by root under LC, and 2 xi omega n is equal to R by L. That's why xi is equal to R by 2 root under C by L. Now another example is, given the system shown in the following figure, find the moment of inertia J and the dashpot constant D to yield 20% overshoot and a settling time of 2 seconds for a step input of torque T of T. Here see, the spring constant is provided, K is equal to 5 Newton meter per radian, torque is provided, T of T and theta is, that is angular displacement, is provided. The respective relations are given. G of S is equal to 1 by J divided by S square plus D by J into S plus K by J. Omega n is equal to root under K by J. Ts is equal to C, that is 2 second settling time. Ts is equal to 2 is equal to 4 by xi omega n, because we are taking for convenience 2% tolerance limit. And see, that's why we can write 2 xi omega n is equal to 4 and xi is equal to 4 by 2 omega n, that is 2 root under J by K. Now omega n is equal to root under K by J. 20% overshoot implies xi, that means e to the power minus xi pi by root under 1 minus xi square is equal to 0.2, that generates xi is equal to 0.456. And since xi is equal to 2 by root under J by K is equal to 0.456, that's why J by K is nothing, that is 0.052. And from the problem statement, K is equal to 5 Newton meter per radian, so that's why we are substituting that value, and J generates 0.26 kg meter square, and xi is equal to C 2 root under J by K, and G of S is equal to 1 by J divided by S square plus D by J S plus K by J. So 2 xi omega n is equal to D by J. So D is equal to is nothing, 1.04 Newton meter second per radian. So after substitution of those all those values, that is after substituting xi omega n and J, we can determine the value of D respectively. Okay. Now these are the respective assignment. When the system shown in figure A is subjected to a unit step input, the system output responds as shown in figure. Determine the values of A and C from the response curve. So here the forward path transfer function is provided, A by S into Cs plus 1. Very interesting problem. You please do it. And another problem is, the closed loop servo system is represented by the differential equation d2c by dt square plus 8dc dt is equal to 64E, where C is the displacement of the output shaft, R is the displacement of the input shaft, E is the error, that is the difference between input and output, that is R minus C. Determine the undamped frequency, damping ratio, percentage maximum overshoot for unit step input, and also find the damped frequency of oscillation. And these are the respective references. I took help from these books. You can study it, and that's all for today. Okay.